Hello students, so welcome to the lecture series on filter design by Edemingo team. So this lecture series will be helpful for GATE and other competitive exams. This will also be helpful for the college students of Electronics and Communication Engineering (ECE). So this is actually the part of signals and systems, and it is also in the GATE syllabus. So in this lecture series, there will be two sections. There are two sections. One is IIR filter design, where IIR means infinite impulse response, and the another section will be FIR filter design, where FIR means finite impulse response. Okay, so we'll be talking about how to design IIR filters and how to design the FIR filters. So we will be talking about, first of all, IIR filter design. Okay, infinite impulse response filters. Now what is the meaning of infinite impulse response? So very simple meaning is that the filter is actually a system, okay, generally an LTI system. So any filter is a LTI system, and if the impulse response of the filter has, yeah, I can say, if the impulse response of the filter is non-zero for infinite values of n, so let us say impulse response, in bracket I write Hn. Okay, so Hn is the impulse response. If it is non-zero for infinite values of n, then it is IIR. And if Hn is non-zero only for few values of n, then it is FIR filter. Okay, very simple. Now one more thing that we can recall, that is, if Hz is the Z transform of Hn, then if Hn is non-zero for infinite values of n, then Hz will definitely have a pole at a finite location, or I can say will definitely have a pole at a location other than z equals to 0 and z equals to infinity. For example, u of n, it is non-zero for infinite values. So its Z transform is 1 upon 1 minus Z inverse. So there is a pole at Z equal to 1. Another example, a to power n un will have Z transform 1 minus a Z inverse, where pole is at a, Z equal to a. So we can say that if Hn is non-zero for infinite values of n, that is filter is IIR, then Hz will definitely have a pole at a finite location or at a location other than Z equals to 0 and Z equals to infinity. So it's a very important point. Okay. Another important point is, so this can be a question, that IIR filters will definitely have a pole at a location other than 0 and infinity on the Z plane. Okay, so this can be a question, or this can be asked in a true or false statement. Okay, something like that. Similarly, an FIR filter where Hn is non-zero, Hn is not equals to 0 for only finite values of n. So in such cases, Hz, that is Z transform of Hn, will have, okay, so I will explain you this. Before writing, let me explain you the statement. So now you recall that Hz, so let us say that Hn is a FIR filter. Now since it's a FIR filter which is non-zero only for finite values of n, so the summation, that is Hz is equals to Hn Z to power minus n, n equals to minus infinity to infinity. Now we know that what is ROC? ROC of Hz is the values of, so we know that Z is a variable that has magnitude R and angle is, or phase is sigma. So let us say this is the phase, I call it sigma. Okay, so this equation can be written as Hz is equals to n equals to minus infinity to infinity Hn R to power minus n e to power minus j sigma n. Now the ROC of Hz is the values of, so let me write it here. Now if you recall the simple Z transform, then the ROC of Hz is the values of R, where the summation of equation number 1 is less than infinity. That is, so I am writing equation number 1, that is this summation. Okay, so this summation should be less than infinity. Those values of R is called the ROC of Hz, where Hz is the Z transform of Hn. So I hope you all know this. So now since Hn is valid, or I can say Hn is non-zero for only finite values of n, so equation number 1 is valid for all values of R except 0 and infinity. Okay, except 0 and infinity. So I can say that, so for a signal Hn which is non-zero for finite values of n will have ROC entire Z plane except Z equals to 0 and infinity. Okay, so this is important. Now as we know the property of ROC, that is ROC never contain a pole. So we can say that since the ROC of a signal Hn which is finite, which is non-zero only for finite values of n, is entire Z plane and ROC never contain a pole, so combining these two properties, that is this property number 1 and this property number 2, so from property number 1 and 2 I can say that the pole of Hz, that is Z transform of Hn, will be at Z equals to 0 or at Z equals to infinity or both only. It cannot be on the finite location. Okay, so this is a very important conclusion for FIR filters, that for FIR filters the pole will be only at 0 or infinity or both, and no finite valued pole will exist. So if I write conclusion, very important conclusion that might be asked in a statement format is that, so here Hn is non-zero for infinite values of n Hn is non-zero for finite values of n. Second, has to have a pole at location except 0 and infinity, means or in a better words I can write, has to have a pole at location other than 0 and infinity. So 0 and infinity can also be there, but there has to have a pole between 0 and infinity also. So next, in FIR we can say that has poles at Z equals to 0, infinity only. Okay, so this is very, very important. Okay, now, so this is enough for IIR and FIR. This much is enough for the information on what is IIR and what is FIR. Now let's move on to the filter design of IIR filters. Okay, now what is this? So how we do the design of the filter? So what is the method? First of all, we design the analog filter and then convert it into the digital filter. So why we do this? Because the designing of the analog filter is very much advanced. So that's why for filter design, first of all, the digital filter is designed in the analog format. So I'm dictating it. So first of all, the digital filter that is to be designed is actually designed into the analog domain, and then the analog domain filter is actually converted into the digital filter that is required. Okay, so here we will be studying, here we will study how to transform analog filter into the digital filter. Okay, now this is very important. This is the motive actually. If you can say that this is the motive of the lecture series. Okay, so this is the motive. Okay, and the question that will be asked will be on this format only, like the analog filter will be given and it has to be converted into the digital filter. And since there are three methods to convert this, we will be studying all the three methods in the lecture series, and that will be sufficient for you. Now, first of all, let's look at the requirements of the. So first of all, let's look at the requirements for transformation. Okay. Now, since what will be given to us, the analog filter, and always the analog filter will be given as in the transfer function format. So transfer function of the analog filter is ys upon xs, and it is given in the format summation k equal to 0 to m dk s to power k divided by summation k equals to 0 to power n 0 to n ak s to power k. So this is the transfer function. Now if we convert this transfer function into an equation, so it can be written like this also. Okay, so if I convert this equation into time domain, so as we know that if yt has Laplace transform ys, then dyt by dt will have s times of ys, and if you do the kth derivative on the left side, so you will multiply s to power k by s. Okay, so this equation number 1 can be converted into time domain. So it is written as ak dk over dtk by yt is equal to summation equal to 0 to power m dk. Okay, so this is the time domain equation of the above equation. So this is the time domain. Okay, now there are three methods to do the conversion. We'll be studying all three methods to convert analog filter into digital filter. We'll be studying all the three methods. Okay, now first of all, let's look at the requirement, because these requirements can be asked in the question. Okay, so an analog filter HAS will be causal and stable. So what is the condition of causal and stable in the analog filter? The requirement is that all the poles of HAS should be in the left half of the S plane okay, all the poles should be in the left half of the S plane. Now if you look at the requirement of the digital filter, for causal and stable, all the poles should lie inside the unit circle. Okay, so the transformation, if you look at this these two statements, this is statement and this is statement, so this is the statement number one, and if you look at this statement, all the poles should be in the left half, lie in the unit circle. So these two statements, if you compare this statement and this statement, then you can say that, so the transformation should be such that left half of the S plane should be mapped into the region inside the unit circle in the Z plane. Okay, okay, plus we can add one more thing, plus the imaginary axis of S plane should be mapped into the unit circle of Z plane. So these are the requirements. So any competitive exam or GATE exam also can ask you in a one marker question these requirements. Okay, so that's why these are important. Okay, okay, so these are the requirements. And now one more fact about, so I left out this, so if I have space, okay, so I have one more comparison which can be done. So let me add a page here. Okay, because these are the notes that I will provide you, so I cannot like ruin them. So that's why in a systematic manner I will shift it downwards, and now I can write it here. So one more difference I want to add here. There is a very important difference between the IAR and FIR filters. Now as you know that IAR filter will have a pole. So for example, let us say Hn is a to power n un. So the Z transform will be 1 upon 1 minus a Z inverse. So by taking the discrete time Fourier transform, e to power j sigma will be 1 upon 1 minus a e to power minus j sigma. So that will come out to be 1 upon 1 minus a cos sigma minus j sin sigma. So this can be written as 1 minus a cos sigma plus aj sin sigma. Now if I write the phase of this IAR filter, so it can be written as into magnitude format 1 minus a cos sigma whole square plus a sin sigma whole square under root, and the phase can be written as tan inverse imaginary part upon tan inverse a sin, I have to shift this more, a sin sigma divided by 1 minus a cos sigma. In the if I take this in the numerator, so h e to power j sigma can be written as 1 upon under root whole square plus a sin sigma whole square, and that will be minus times of tan inverse a sin sigma upon 1 minus a cos sigma. Now similarly, if there is a pole, a finite location pole, whenever there is a finite location pole in Hz, then in no case you can get a linear phase of Hz or a linear phase of h e to power j sigma. You will never get that. So what is the meaning of linear phase? The linear phase means, let me add one more page. Okay. Okay. So the linear phase means the linear phase of Hz or h e to power j sigma means phase is of the format a times of sigma. Okay. Okay. So phase should be of this format where a is any constant. It can be positive or it can be negative, but it has to be in this format for linear phase. And thus, whenever we have an IAR filter, Hz will have a finite location pole, or by this word finite location pole, I mean that there will be a pole between z equals to 0 and z equals to infinity always, and thus h e to power j sigma will never have linear phase. Thus we can say that a realizable IIR filter will never have, or I will just write that statement, that will always be true. Okay, so the statement is physically realizable and stable IIR filter cannot have a linear phase. Okay, but the FIR filter can have that. So we'll be looking at what are the conditions for FIR filters to have a linear phase, but in the later part of the lecture series. But till then, this is a statement that will be true. If you find this kind of statement, then it will always be true. Okay, but this can be asked in any of the GATE exam or any other competitive exam also. So we have done till here. So thank you guys So in the next part of the lecture series, we will be starting with the three methods of converting or realizing the IIR filters. So thank you. Keep sharing the videos and keep giving us the feedback so that we can improve ourselves. So thank you guys.